Now that you've seen a couple of examples using conservation of momentum, we're going to try one which happens in 2 dimensions. So we're going to have some objects that are going to eventually move with some x direction and y direction things, showing how momentum is still going to be conserved. So, starting off with this question, consider a mass of m moving to the right with some initial velocity v naught. It's going to explode into 3 equal pieces. The first piece flies off vertically with some unknown velocity v1. The second flies off horizontally to the right with some unknown velocity v2. The final pieces fly off at an angle of theta below the horizontal with a velocity of v3. So the goal is to find the velocities v1 and v2. So before we solve this, there's a lot here, so I'm going to try to draw out a picture of what's going on here. Just like Dr. Wu's previous video, we want to get that initial state and final state in the setup. So we have a large mass m, and it's going to move to the right with a velocity of v naught. So that's kind of we'll call this our before state. And then after, let's see here, we've got 3 pieces. I'm just going to draw them. Okay. And it's splitting into 3 equal pieces. So I'm going to take this mass and basically divide it into 3. So all of these, the mass is just m over 3. Okay. So I'll label that. Okay. So the first one's going to fly off vertically with a velocity of v naught, or v1, going up. Second one to the right with a velocity of v2. And then the third one's going to be going at an angle with a velocity of v3. And theta is noted as below the horizontal. So that is our kind of before situation, after situation. In terms of the type of collision here, when we think of a collision, we usually think of things that are running into something else. In this case, it's kind of a reverse, perfectly inelastic collision. We start off one object going together, and then that object separates. So it's an explosion. It's kind of the reverse of the collision in this problem. So let's go try to solve this mathematically now. So now we're going to set up the conservation momentum equation for getting us used to the math for this. So one thing different with this one versus the previous couple of examples, we see that we don't just have a couple things that are crashing, head on, or they're moving both vertically. We've got a mixture here of dimensions. So momentum is still going to be conserved, though. That rule still applies. We just have to think about 2 dimensions now. So we're going to be able to conserve momentum in both the horizontal direction, which is, we can see that the V2 would be something that's horizontal, the V naught's horizontal, we're going to have pieces here, and then we'll also have things that are going vertically afterwards. So it will be conserved in both of those dimensions. So writing the conservation equations in both directions, I know that initial momentum is going to be equal to final momentum, okay? And then we're going to do this for 2 dimensions. So I'm going to have one of these for the x direction and then another one for the y direction. So I'll do one more of these. Okay, so we've got 2 dimensions to keep track of. So looking at our initial setup, that our initial state is here where we've got our large mass, our combined mass, moving to the right. So if I think about defining my axes, this one's, if we have a coordinate axis, we'll have our positive axis going to the right, positive y up, and then the negatives are opposite of that. So I can see that in the beginning, we only have a mass that's moving to the right, which is in the positive x direction. So all of the initial momentum is going to be associated with the horizontal dimension instead of the vertical. So my initial side would be capital M V naught for the x direction, and then for the y direction, we have actually nothing. So the initial y is going to be 0 equals, just to be clear, for this one's for the x direction, And this equation's for the y direction. Okay. All right. So now looking at what happens afterwards, the final part of this. So horizontally, I want to look at everything that's moving right or left, because that's going to be the after here. I can see that the first mass just goes straight up, so that won't be involved. The second piece, I should say, is going straight to the right. So I'm going to have that m/3 for our mass times v2. Okay, I'm leaving it as a positive thing because we've defined to the right as positive. Then I look at the third mass here. It's going down at an angle. So remember with vectors, there's going to be an x component associated with this. That's our v3x. Okay, and then it'll also have, I can go ahead and draw the y component in too. We'll have a y component that's going downwards. Okay. So my x component here, it's also moving to the right, so I'm going to add these two pieces together and say m/3 times v3 cosine theta. Okay, so that'd be our equation in the x direction. Now we want to do the same exact thing for the y direction. For the final, my first piece goes straight up vertically. We'll call that the positive direction. So we'd have m/3 times v1. And then I notice that the third piece here, the only other one that has vertical motion, is sending the object overall in a downwards direction. So I need to subtract these instead of adding. So I'm going to subtract m/3, and then I'll use sine theta to get in the y direction. So that is where we're going to start the conservation part. And then from here is where you can start plugging in numbers and rearranging to solve. So I'll do that in the next step once I have a little bit more room. So here's our equations for initial and final momentum for both dimensions. All right, so here's our two equations that we just set up in the x and y direction. Now we can start rearranging to figure out what we're solving for. Remember in the original question, it's been a little while since we've done that, but in the original question, it was asking us to figure out what v1 and v2 are. So I'm going to try to rearrange these such that we're solving for those variables, even though we don't have numbers to actually substitute in. You could substitute numbers if you wanted to. Okay, so first thing I notice here, we've got m/3 in both terms, so I can kind of combine those, move them to the other side. So if I multiply everything by 3, so then that would cancel out those, so I'd get a 3mv0 over here. Then that'd leave me with m times v2 and m times v3 cosine theta. So then I can divide by m on both sides. And then that leaves me with v2 plus v3 cosine theta. And we notice here that the mass portion ends up canceling out. So we don't really need to know exactly how large the substance is, but we just need to know that it splits into 3 equal pieces. So that's kind of helpful there. So now we can just get v2 by itself. So I'm going to move this piece to the other side. So we've got 3v0 minus v3 cosine theta is equal to v2. And then there's one of our equations we can work with. So if you knew the third, so this one was a known value, you could plug it in, theta was known, and v0 was known. So these are all knowns, and then that would give you v2. Just a note about this too, this is something in the x direction, and we're told that we're moving to the right, so we should end up, when you math this out, you should end up getting a positive answer. If not, that just means that this is incorrect, and it actually should have been going in the negative direction. But again, if you get a positive number for this, then that means it goes with our original coordinate system that we're setting it up to the right. Okay, so in the y direction, now we can use this one to solve for v1. It's all by itself. There's a 0 here, so I'm just going to move this negative piece to the other side. So we'd get m/3 v sine theta is equal to m/3 v1. And then we can see here that the m/3 is on both sides of the equation. We can cancel that out. So we're just left with v3 sine theta is equal to v1. And again, this should result into being a positive answer, okay? We've already accounted for the negative up here because this object was going downwards in the final. So this should turn out to be positive because that's what we know is happening to that final velocity. So at this point, if you wanted to, you could plug in some numbers, and we have our final velocities in both directions for those unknown objects. And here you have it, a two-dimensional conservation momentum problem.